Alright, so on the previous part for this section we covered the integration of functions involving powers of sines and cosines. I'm going to move on through this by looking at powers of tangent and cotangent or secant and tangent. Well, I believe the strategies for sines and cosines are the ones that for sure are going to work like the way they're described on the definition box. However, when it comes to tangents and secants, sometimes those are gonna give us some trouble every once in a while. All right. Well, what happens for secant powers that are even? Well, in this case, we need to save one factor of secant squared. All right. If the power is even, save one factor of secant squared. Well, guess what? Why do we use that power of secant squared that multiplies the dx? That's because secant squared would be the derivative of what function? Tangent, and then we would use this identity to represent everything in terms of tangents. All right, in just the same way that we used that we save the power of sine and leaving everything in terms of cosine. That's because those cosines, the derivatives are sines, and that's the u du part. So same here with this. All right, if the power of tangent is odd, well, in this case, save one factor of secant tangent, because secant tangent is the derivative of what function? Secant. So, and in this case we represent everything in terms of secant. So when our u is secant, its derivative is secant tangent, and that stands the u du part of the problem. All right, let's have a look at one example. Oh, by the way, this one will be a definite integral. So, well, it's going to work the same. I mean, do all the necessary algebraic techniques, or, well, in this case, trigonometric identity manipulations, and then we use the fundamental theorem at the end. That's pretty much all it is. All right, so what do we have? We have an even power of tangent. That's the one that we need to convert to, let's see. Okay, what do we have? Oh, that one is going to be interesting because we have secant even and tangent odd. Well, number one, do you see a not power of tangent? Well, we have an even power of secant, so that's the one we're going to work with. So we're going to save one power of secant squared. That's going to be the u du part of the problem. So I'm going to rewrite the integral from 0 to pi over 4 of tangent to the 6th power. And I'm going to rewrite secant squared times secant squared. And I'm using this color to represent what we later will work out as the u du part. Alright? So from here, the remaining secants, this secant squared, we're going to use the Pythagorean identity that involves secant and tangent. Let me write it at the top. So that identity is secant squared equals 1 plus tangent squared. So this quantity right here will replace the whole secant squared on the integrand. So that's the integral from 0 to pi over 4 tangent to the 6th times 1 plus tangent squared times secant squared. And notice how we're going to end up with a polynomial of tangent whose u will be tangent, the derivative of tangent will be secant squared, which is what we have in this shade of green. Alright? So let's see. Tangent, let's distribute this, integral from 0 to pi over 4. That's a tangent plus tangent to the 8th secant squared x dx. Okay, and in this case we're ready to do the u substitution. U equals to tangent du secant squared x dx. And well, in this case no numerical factors are needed. I think this is fine. This is enough for the u du part. So this will be the integral of u to the 6th plus u to the 8th du. And I'm going to skip the limits of integration. Yes, I could have done the changing the limits. That's fine if you want to do it. But this time I'm going to do the limits in the end. It's fine. So this one reduces to, or integrates to u to the 7 over 7 plus u to the 9 over 9 plus, well, so let me leave it like this without the c. And then back substituting, that's a tangent to the 7 over 7 plus tangent to the 9 over 9, evaluated from 0 to pi over 4. Right? And then the rest of the problem is just a fundamental theorem of calculus. Evaluate upper limit minus lower limit. So that's a tangent of pi over 4 raised to the 7th power over 7 plus tangent of pi over 4 raised to the 9th power over 9 minus, okay, do we agree that if we plug in a 0 for these two terms, what's tangent of 0? 0. So how about a big 0 here? No need to write those for the ones that are kind of obvious to be 0, no need to show. Just so you can save time on your writing. That's fine, that's valid. But what's tangent of pi over 4? 1, so that's 1 to the 7th over 7 plus 1 to the 9 over 9, which is in this case 1/7 plus 1/9. And combining like terms, well, simplifying these fractions, we need an LCD. So that's 9, 9, and 7, 7. Final answer, so that's 9 plus 7, is that a 16? 16 over 63. Alright. So again, it's basically the same idea, but in this case it's which trigonometric identities are going to come in this case. Alright, so let's look at the next example. The integral of tangent to the 5th power times secant to the 7th power. Well, in this case we have odd powers of both functions. Let's see what do we have for odd powers. So on the guidelines right here, whenever the tangent function is odd, we need to save a factor of secant tangent. Well, of course, we need to have some secant there in order to do that, which of course we have. So what we're going to do in this case is, I'm going to rewrite this integral of tangent to the 4th secant to the 6th and secant tangent. That's the du part of the problem. That means in this case we need to express the factors in blue in terms of a function whose derivative is secant tangent. And what is that function? Oh, secant, right? So the derivative of secant will be secant tangent. So we need to express everything here in terms of secant. All right, so let's have a look. So yes, we're going to use that trigonometric identity. The one that says, okay, what was that? So let me use it. Secant squared equals 1 plus tangent. Okay, so we're going to use this identity, but in this case we are going to replace all tangents in terms of secants. That is, tangent squared x equals secant squared minus 1. So, well, in this case, the tangent to the 4, I'm going to write it as tangent squared quantity squared, the same way we did it before with the sines and cosines. So that's tangent squared and secant to the 6. So from here, tangent squared, oops, this is going to be replaced over here. So that's the integral of secant squared minus 1 squared times secant to the 6 secant tangent. All right. Okay, what do we do from here? Well, number one, of course, we need to expand this binomial. So you have a couple of options here. You might want to do the u substitution from here, so when you do the expansion of the binomial here, you don't have to write a polynomial in terms of secant, or you can leave, which is what I did in the previous example before, the one for sine and cosine. So in this case, it's fine to do the u sub, or at this point, where u equals secant, or actually secant theta, du equals secant tangent, which actually doesn't require any factors here. And well, in this case, we can write the integral as the integral of u squared minus 1 squared u to the 6 du. And instead we can expand the binomial in terms of u, and not a binomial in terms of secant like we did before with sines and cosines. So let's expand the binomial again. We're going to do a minus b squared, a squared minus 2ab plus b squared. And then from here, u squared squared, that's u to the 4th minus 2u squared plus 1, that multiplies u to the 6 du. And then we can simply distribute the u to the 6 to each term inside of parentheses. That is, okay, u to the 4 times u to the 6. Isn't that u to the what power? U to the 10th, u to the 8th, and u to the 6th. And well, we can integrate these three using the general power rule. That's u to the 11 over 11 minus 2u to the 9th over 9 plus u to the 7th over 7 plus c. And well, of course, now we need to go back and substitute for u, which in this case, secant to the 11th of theta, 1 over 11 minus 2 over 9 secant to the 9th plus 1/7 secant to the 7th. All right. Any questions about this exercise? I'll leave it here so you can see the whole problem in case you missed anything. Are we ready for the next one? Question? Yes?
How come we start with secant to the 7th, but then we have secant to the 6th power?
Secant to the 7th. This one?
The equation is secant to the 7th power.
Oh, okay, so in this case, because the power, the power of which one is it? The power of tangent is odd. We needed to save a power of secant tangent, so that stands the du part of the problem. So if we initially had 7 secants, when we save one of these, that becomes one less, like by properties of exponents, laws of exponents. This is a 6 plus 1. 6 plus invisible 1 becomes a 7, and 1 invisible 1 plus 4 equals 5. But we arrange it in a way that we end up with a secant tangent which sends the du part of the problem. All right? Okay, so the issue with the tangent and secant, the powers of those functions rather, those guidelines typically are going to give us some trouble sometimes. They're not like very straightforward like the sine or cosine. If you have sine or cosine with an odd power, well, save one power of whatever the case, represent the remaining powers in terms of the other function. If you have even powers, well, power reduction formula. Those are always going to work for sines and cosines. However, there are some cases in which we may need other integration formulas, the ones that you may have. But well, of course, you cover back in Calc 1, and I'm gonna use these two integral formulas to refer for some of the exercises here. Okay, so let's evaluate this integral. Let's see.